Okay, I think we are in a position to do more in set. Last time we talked about definition of a set, and we said that set can be defined using two methods, the roster method, the set builder method, and we talk about the power set, the set of all set. We talk about the universal set that every set is a member of, and we also introduced the Cartesian product, how to form pairs. Given two sets, we can create pairs, or in general, we call them tuple. So today we're gonna do more. We're gonna do operations, some operations on sets. So the operation that we will be talking about is the set union, and it will be similar to doing addition in arithmetic, and then in set intersection, okay, which is very similar to having the AND operation in propositional calculus or multiplication. Set complement. Okay, let's think maybe the closest thing is, of course, this is just analogy, right? So we know if there are some duplicate of element of a set, then the duplicate is not considered. But again, so what I will say here, they are similar to these, but take these with a very huge grain of salt, right? Just to get us started. And then set the complementation. So you can think of it in terms of arithmetic of having an upper level number, and then we do subtraction. So to what complement that? For example, if the biggest number I have is 100, and I want to get the complement of 7, so the complement of that will be 93. All right, and set difference is like subtraction. Last time also we talked about cardinality. We're just talking about the number of the element in a set. So we're gonna do more on that, and then we'll talk about identity. What that means, given some term involving these operations, when that term is equal to some other term. Let's say this is term, and we have another term. Let's call it a term prime. So that will be useful in doing proofs. And finally, we're going to introduce a method that is similar to truth table in propositional calculus, but this time involving sets. The set theory and the topic that we spend a lot of time talking about, propositional calculus, are now part of the field called Boolean Algebra that is discussed in chapter 12 in the book. We will not cover it in this course, but you're free to go and read. But if you have done the computer engineering course, then you would remember. In what is important for us is this system, this algebra, deal with quantities like zeros and one, and thus define some operation, addition, multiplication, and so on these. When we also introduced propositional calculus, we did something similar. We defined operation, and the operations were the and, the implication, the or, the negation. So these kind of operation. If you recall, when we covered propositional calculus, what matters for us is the truth. So there was some sort of binary result, something either true or false. Okay. With Boolean algebra, we have either 0 or 1. So you can see that the binary thing that is common to both. And in set theory, we have some element, okay, either in a set or is not in a set. Okay, so you can see these three things, they deal with something in some binary sense. And when we deal with sets, always we always assume there is U. What that means, the universal set. Using Venn diagram, if you recall, we represent that as having some area. So we think this is our universe of discourse. If you recall from Tarski's Wall, the software we use for propositional language, in the graphics, the space was in front of us representing the whole universe. So same thing here. Every time we talk about, for example, set A and set B, they are somewhere here. This is A, this is B. We assume there is U, there is universe, that all part of. So this is the whole thing. Think of it as the globe, right? And all countries of the world are part of. Here is our first operation, which is called the union. So the union is defined this way: the set of all x, okay, such that x is in A or x in B. So again, this is an example of set builder. And set builder, we said, right, it has two parts. The first part lists the element, in this case x, and here put some condition. Right? Is like saying, okay, what this apply to this condition. Let's say I'm going to talk about the set of student. Okay, I'm going to say x. So without the condition, anything can go. Anything can go. But when I say x is student, then I'm talking only about students. So this part is they provide the condition, and sometimes we just use some predicate, p of x. In fact, this is really a predicate. All right. So how we read it again? The set of all x such that this one you read such that x is in A or x is in B, and this one is the inclusive or, which means from our understanding, for our discussion of propositional calculus, that it's mean when this one is true is when either or both. So the element in the union could be coming from A, from B, or from both. The crucial thing is this, how we write that is the A union B equal the set. So this is really a set. This is really a set. Pretty much like having 2 plus 100. What I'm going to get back, this number plus number, what I get back, I get number. I get number back. What is the number I'm going to get is 102. So given 2 set, I get the union, I get back a set. I could have named this one W, right? But just a set. This is a new set. And here is an example. So if I have this set, okay, let's say I have the Venn diagram. I have here the first set. Let's say I have here 1, 3, 2, and the other one is here. It has 3, 4, 5. So what I have now, I have this common set. This is the whole thing. This I have now a bigger set, and of course they are part of some universal set, some bigger set. The second operation is set intersection. Set intersection. And this operation collects the common element. So if I have set A and B, the resultant, the result set, and we write it this way. So then A intersection B again is a set of all element X such that X is in A and X is in B. All right, so using Venn diagram, I'm talking about this area, the elements that are in common. And by now you will see the connection between this symbol and this symbol. And in the previous slide, we saw the connection between the union, which is this form, and the OR operation in propositional logic. And this similarity is not coincidence, it really invoke that kind of connection, the OR. Here is the AND. So this is just talking about the common element. So if I have a set, okay, if I have a set, a first set, it has element 1, 2, 3, and the other one has 3, 3, 4, 5. So before we have this is one set, and this one is another set. Okay, then we are talking about the one that happened to be in between them. So in this case we have 3 that is common to both. All right, so if we have set the intersection of the set 1, 2, 3 and 4, 5, you can see there are nothing in common. So for example, here the first one 1, 2, 3, and the other one has 4, 5 and 6. You can see there is nothing in between them. There is nothing in common. So it is really empty, right? So this is indicated by the empty set. Set complement is written in two ways. You can write it as a bar, like you see it here, or using this convention. Some books use this one, is always with respect to some universe. So although we might write it this way, say a bar, to be the set or the a complement to the set of all x such that x is in U, all right, and the set of all element x in U such that x is not in A, right? So what is really mean is that the set of all elements that are in U but not in A. So maybe another way to read it as x in U but not in A. Yeah, this is why you can see there is a sense of and. So I can write it. I could have written this one as saying the set of all x such that x is in U and x is not in A. It is the same thing. All right. So, but what we have to keep in mind is this operation is relevant to some universe of discourse. So if we are talking about if U is the set of all positive integers less than 100, then the complement of here we have the set of all x such that x is greater than 70. What is the negation for that? So remember, you're going to take this guy here. What is the negation of x greater than 70? Will be x is less than or equal 70. right? And they return this way. So this is the complement. So the set of all elements such that x is less than 70. So using Venn diagram, this is the what I'm interested in. I'm not is like what is really saying here, a u but not a, or this is the same as saying a bar or a c. All of them mean the same thing. What really I'm not interested in the element of a. I'm interested on the element that are outside of a. Okay, that are all my I'm interested in. I'm interested in everything in the universe, but is not a. That's what it really means. All elements that are in a and in u in the universe Discord, but they are not in a. I'm not interested in the element of a, and this is why you see it in white there. Set difference is our next operation. Is very similar to the complement, but this time instead of the complement with the relevance to the universe, we're talking about some other set. So it was, or maybe a better way to say when you have something like that, a minus b or difference b, is you can think of it as a x is in a but not in b. So again, this is really a set. It defines a set and how we write it. Okay, the set of all x such that x is a and x is not in b. That's what really, but not. All right, the same thing. So you can write it this way or this way. All right, and you can see here the connection to the end. And using the Venn diagram, what it really mean? What really said? I'm interested in the element that are in A, okay, but not in B. So anything in common or in B proper, I'm not interested in. I'm only interested in the element that are in this part. You can see it here in blue. The cardinality of a set, which is simplified using this simple, just two bars. So given a set A, and here I'm asking about the number of elements in A. So if A, let's say A has element 2, 1, 7, then the cardinality is 3. You're talking about the number. Yes, like I don't really care about what this set represent. I'm really interested in the number, like using the symbol with the absolute value for recall. It's like, you know what, I don't really care about the polarity. I'm just talking about the number. So in a similar way here, using this symbol to indicate cardinality is saying, you know, I don't care about what things are within A. I'm only curious about the number of elements. All right, so that should be enough. So now we know this is the set union. This is the set, is a set that consists of elements from A or B, and here we want to know how many elements. And the rule here says is the element of the union is equal to the element in A plus the element of B, and subtracting from that the common one. And this is really crucial, and it goes by this fancy name, the principle of inclusion exclusion. It is crucial, and it is important as you study probability theory. You will come across that for sure, and it's really nice way of alerting us to be careful of double counting. So let's say, for example, that in some department we have some faculty, all right, and the faculty is like you want to say, you want to know if you have the union, let's say A representing the faculty and B representing the graduate student. So if you say, all right, I want to see the total, how many of these, if there is a sharp distinction between the two, what that mean? If no one can be in both, so what if we have, let's say we have a rule that no graduate student can be member of the faculty, then it is fine. But in some, that is not the case. In many schools, you will see there are some students that play both roles, being part of the faculty and also their student. So if we don't do this exception, then we're gonna get into trouble. So we have to say, all right, these are the graduate student or the faculty plus the graduate student, and the one who are doing both, we don't want to count them twice. So we're gonna exclude this from the count. Another example is here. So let's say I have A representing the representing X is maybe math student. X is math student. And I have B to mean what? X is computer science student. But we know that some students are really doing both, all right? So if I have A, it has, let's say A have 5 students in it, and B has 6 students in it, then I want to say, all right, the total then will be A union B will be A plus B. Okay, and in this case I have 5 and 6 are going to be 11. But let's say there are some students that are doing both. Okay, they are doing both. Then I need to find the one doing both. So A intersection B. Let's say there are 3 of them. I need to exclude that. I need to exclude that number. Then I will have this 11 minus 3. We're gonna be 8, right? Where before that gonna be give me the wrong answer. So this rule is important to prevent us from making the error of double counting. So later in later chapter we're gonna see a general format for this rule, is the inclusion or exclusion involving more number of sets, but for now that should be enough for us to understand why we have to have this one. Okay, but in this example, let's say there are no students doing both computer science and math at the same time. So on this one will be just 0. Okay, and the result will be 11 is correct. Let's take some example. So here we have the universe of this course is the set of natural number from 0 to 10. So you see it here in front of you. This is the whole thing. And then we have other set. We have A. Okay. A consists of 1, 2, 3, 4, 5. Let me just demark this area. So this is A, and we also have another set. Okay, we have B. It has 4, 5, 6, 7, 8. So this part here. So this is B. Okay, so then we have some questions, and the first question says, what is the union? Okay, and from our understanding, the union is the new set, a bigger set, Okay, that is composed of all elements of A and B. Okay, so what that set? Okay, it's this set here, you can see it here. I'm going to use dotted to mark it, right? And you can see its element here. All right, so what are the elements that are in common between both? Okay, let me just use different color. I'm going to use yellow here. So it's talking about the set intersection. Okay, and the set intersection is the set here. Here you can see it here. That is, let me use another color, so it's really show the blue is not really showing. All right, so this, so the element that in both. Okay, so that should be 4 and 5. The element, the complement, the element that belong to the whole U, but they don't belong to the to A. So that means these are A. So we're looking at everything outside of the boundaries, outside the green lines. So let's see what that are. So it's 0. These belong to the U, the bigger set, 9, 10, and the element that in B but is not in A. So it's the 6, 7, 8. So the only thing is left is the element that belong to A. How about B? It's gonna be all elements that are outside of the red line. Anything outside the red line will be the complement of B. All right, A, but not B, gonna be the element that in A, right, but not in B. So what that means, we'll be talking about this area here. Okay. How about B? B but not in A, the other way around. So I'm gonna use this line. So we're talking about this area here. Okay, so elements that are in B, which is 6, 7, 8, but not in A. Something is not essential, it's really derivative, is that this symmetric difference. So if this is the cousin of the exclusive OR. Remember the exclusive OR in propositional logic, all right? So we say some things have proposition P and L, then it is true only in the case when you have this is true, this is false, or this is false, and this is true but false otherwise. So this is really the same thing. Okay, so it is the element in A but it's not in B, or the element in B not in A. And also, if you recall this from Boolean Algebra, also we did that. So how we mark this? So this part represents the element that in A but not in B, and this is the element that in B. I'm gonna use straight line, vertical line, that in B but is not A. All right, so the union of these. So this is why I have them the same color. So the first part is talking about this here, this half. So it's talking about this. And this part is talking about the other. I know it looks like a crescent. And then here's some operation. What that means, I'm talking about all of them, right? With the exception of this area. All right, so if we have the universe, okay, if we have the universe to be as before, okay, then the symmetric difference between A and B are the element that anything other than the elements that are in common. So if you recall from the previous slide, the one in common were 3 and 4. So the 3 and 4, the 4 and 5 will be excluded because they are what they have in common. They have 4 and 5. 4 and 5 in common. These ones are not included in the final result. Okay, let's introduce some identity that will be useful in doing proofs involving sets. And these identities are straightforward or they follow from the definitions of the union, intersection, and so on. So the first one says that given two sets, one of them is the empty set. So what is the union of that? Is that set, the other set. So we know for sure this one is empty. So what is the union? Remember, the union says is the set of elements that are coming from A and from B. All right, so we know this is empty, then it must be the element that's from A. And this also involves even the case when A itself is the empty set. Okay, so the empty set union the empty set is the empty set itself. Okay. All right, and another identity here is the intersection, the common element between some set and the universal set. We know that given any universe, this is the universal set, then that set it must be a subset of U. So U is the biggest one. So what are the common elements between them? A itself, right? Because this is the U is containing all elements. And so in other words, I can say A, or I can say A intersection U. They all mean the same thing. Domination law says the union, if you have the any set and its respective universe, then it's gonna give me just the U, all right? And again, the reason for that is we know that when we get the union of two sets, repetition is not allowed. That's by definition of a set. Although here are some element, but we know they are member of U, so they will add nothing. So what really says here, if I take some subset A from U and I put them together, I'm not adding anything. It's just another way of talking about U. All right. Similarly here, if I'm talking about the common element between any set, given any set, I want you to think of these A and B just saying for any A, or any set A. So any set A, what are the common elements between that set and the empty set? Nothing, because the other one is empty. Again, this is including the case when this one is also empty. This one is very similar to true or any proposition. It's always true. You can see the similarity between this law and the laws that we talk about in propositional logic. Okay, so because this one is nothing else to do, and here is like saying the P and the false is always false. So yes, you can see the similarity between the two, but they all the meaning comes down to the definition of the respective operations. Okay, and if the idempotent law says the union of a set with itself, what are you going to get back? A set itself, because we say repetition, that doesn't matter if I have a set A with element 1 and 2. Okay, we said this is the same as saying 1, 1, you know, a million times repeating the 1, comma, 2, 2. It doesn't really matter. All mean the same thing. Okay, so there is no multiplicity here. It's just we know that a set is a subset of a set if they have if the first has the same element in the second. Okay, same thing here with intersection. The common element between any set and itself should be itself. Okay, and finally here the complement is like the double negation, right, in propositional logic. Okay, so again, give me back the set itself, the complement of the complement. So you remember, if you have this is the universe of discourse, and this is A. Okay, we say the complement is this. Okay, the complement is this. Okay, this is A complement. Now, what is the complement of the complement? All right, then you're gonna give me what? Then I'm not talking about this. Like say, I'm not talking about this. I'm talking about anything that is not this here. So what that means? I'm talking about A itself. These operations, like addition, multiplication, arithmetics, they have some properties. One property is commutative. What that mean? When I say A union B, the same as B union A, the same goes for the intersection. And this is true even for arithmetic. So I can 2 plus 3 is the same as 3 plus 2. What that means, the order doesn't matter. Same thing go for multiplication, whatever. And then here is the associativity law. What really says here that the putting the brackets or the order operation doesn't matter. Okay, and so maybe the best way to think of that is to look at some example in arithmetic. So I have 3 plus 2 plus 5. I can add these first and then add the result, or I can do the other way around. I can add the 2 and 5 and then I add the result. I'm gonna get the same thing. And this is exactly what this result really says. Okay, so the in short mean that brackets are not really important. Okay, the same thing goes for the intersection operation. And here maybe a little bit of involve a little bit more of need some thinking, which is just the distribution. It really says that that intersection can be distributed over distributed over union. All right, and the union also can be distributed over the intersection. So maybe a good example from algebra. So if you have something like this, 3 x plus y. In algebra, this is the same as saying 3x plus 3y. Okay, they mean the same thing. And this is going to be useful in doing some proof. We also have the De Morgan law. De Morgan law we introduced it when we talked about the proposition calculus, and it helps us negate something like this. If I have P or Q and I want to negate, it tells me how to negate, and also it tells me how to negate intersection on this, I mean the conjunction. Okay, and you can see the similarity. So what is the complement of the union is the complement of A, the intersection of complement of B, and you can see really similar, very similar to the way we use it in propositional calculus, not P or not Q. So I hope, I hope we're gonna go fast on this one because you're already familiar with it. But again, gonna come handy and very useful. Absorption law, where is something, this one is really can follow from the laws that we mentioned before. And again, there are some similar to it in propositional logic. So if I have A union the intersection of A, B, this is the same thing as saying A. And similarly here, A intersection, the union is also A. But again, maybe you can do it as homework. You can see that really is follow. It's not really some distinct, some is derivative. You can derive it from others. A complement law. So when you say here A, the union of A complement, you're really talking about the U. This is the same as saying in propositional calculus P are not P. And we know this is what is always true. So what that means here, when you say set A and its complement, is really talking about the whole thing. So in other words, if this is U, and you have here A, okay, so we know this is A, this is not A. But when you put them together, this is the union. What I get back is the U, the whole thing. Okay, so the common element here, the common element between A and its complement, by definition, there is nothing in common between them. So just the empty set. Now that we have accumulated a lot of understanding of the identities and properties of set operations, we're ready to do some proof. And the way we do the proof is, especially in the case of showing something equal to something. Let's say you have two sides. This is the left-hand side, and this is the right-hand side, and both involving some operation, union, intersection, complement, what have you. So how do we show that they are equal? So we're going to show that we're going to assume there are some element x is in the left-hand side, all right, and x here is going to be arbitrary element. So we're going to show that from this. We're going to show also that x happen to be a member of the right-hand side. So in other words, what we will be doing is showing that the left-hand side is a member of the right-hand side. Okay, but that's not enough. That just tell me this element in this is also element in this. I also need to show that the right-hand side is also a subset of the left-hand side. If I show these two, then I just showed that the left-hand side is equal to the right-hand side. All right, but we start by saying, okay, let some element x be a member of something, and then because we chose this to be an arbitrary element, okay, then that's true for everyone, and this is how we show a membership. Then we're going to do the set builder or some rule, or we're going to use the membership table, and we're going to have some example to that effect. Let's consider this example. So we have this identity, is not yet identity. We want to show it's really identity. We're going to show they're really equal. All right. So again, the plan is we're going to do two steps. The first step is to show that the left-hand side, which is the complement of the intersection, is a subset of the union of the respective complement of both A and B. This is step one. This is not complete. This is just showing that it is the left-hand side is subset of the right, and then we're going to do the other way around. If we succeed, then we just showed that they are in fact equal. What that means, they got this every element in here is if you take any element here, we'll find it here, and vice versa. All right, so what's gonna be the first step? The very first step is we're gonna say assume, okay, x, some arbitrary element, some x, right? But assume it is in this guy, all right? If you still have some confusion about that, you can think of this one statement is the definition. All the definitions we studied, all of them have something of like of the formula for any x, all right? And then remember what we do. We do universal instantiation. So this you can think we use that. You said x, or you could have said any letter. But this is example of universal instantiation. Okay, so we pick some arbitrary element. We just, because it's true for about anything in the domain, we're gonna pick x. But here's crucial: x is in the domain. X is in U, right? So we're gonna pick that and say, okay, assume it is in this, all right? And then see what happens. And what we do from this. So we're gonna appeal. We're gonna appeal to the definition of the complement. Okay. So I want to get rid of this, right? And we're gonna appeal to a definition of the complement. All right. So in effect, we'll see here. I'm gonna go using the definition, and then every step will lead me to the logical component of the definition. Let's proceed. So what it means to say x is not in and b? It really means, if you go back to the definition of this, if you unpack this, what it really means, x is in a and x in b. This is the definition of the intersection. Okay, this is the definition of intersection. And the negation here, we did two steps. This means it's not the case. So how are we going to read that? It's not the case, it is in the union. All right. Oh my goodness. Now we have something that is familiar. What you see here, what we see here is our old friend propositional calculus statement. It's like having P, this one, remember this one is when we say X is in big A, it's just proposition. It's like having something P and Q. So these can be what, either true or false. That is crucial. And you can see evidently by having this conjunction. Okay, so what is the guess we can do? So we have here, we have something like this, and we have something, some negation there. What rule that helped me do the negation? Of course, De Morgan's. Right? So I'm going to De Morgan, and then it will help me with simplification. All right, so just you can see here, right? And this one negation become here, and this one turn into or. Okay, what else we can do? So this one will be the same, but this one we will gonna appeal to the definition of the negation. So this is what it says. It is not the case that x in A. This is the same thing. Okay. But this, it means the complement. It means x is in U or x in B. But this one, this last line reminds us of a definition. This is just the definition of the union. So x is in the complement of A, or x is in the complement of A union B, and this is just the right hand side. Okay, so this is one way. Now we're gonna do the opposite, right? We're gonna say, okay, let's again, this is like universal instantiation. We don't say it; it's understood to be. So x is in the union, and this is gonna be the assumption, So what that's really mean, it's something in the union. What is the definition of union? This is the definition of union. And then I go and unpack this using the definition of complement, negation, okay, and then here I have the Morgan's definition of intersection, and finally I got what? I got the left hand side. I got the left hand side. So what we have done here, we showed that the left hand side is a subset of the right hand side, and the right hand side is a subset of the left hand side. Therefore, the left hand side is equal to the right hand side. Okay, and that's complete the proof. And here is the same proof, but using set builder. The set builder, if you recall, have the two parts, is the indicating the part that indicate the element and the condition, but the condition is really just a definition. So you can see it's not really the same thing as the as we did before. So what the crucial thing that you see from the proof is that really we appeal to the definition, where then we arrive at some proposition, and then we just use the laws of logic, okay, use the laws of logic, and we go back and wrap them again and use the definition to end up with set. So maybe the best analogy to think of what we have done here, this is, you can think of this one as some wrapping. So we want to unwrap it. So when you do the unwrapping, result in the internal structure, which is just built on logic. And then after we're done, we just put the wrapping back again, and we get the same thing. So you can see started from one side and then the other. I could have started from this way. In fact, you can say, okay, assume X is in this set, and then you can go backward. It gives you the same thing. Here is the final way of showing some relationship, and this is very similar to truth table. In fact, you can think of it as truth table. Okay, so in this case, how many sets we have? We have 30 sets, and because we have 30 sets, then how big is our table? We're going to be 2 to the 3, which is 8. Again, you can see them here. So the 1 represent X or some A is a member in some set. Let's call it, I don't know, big X. So this is 1. If A is not member, then we say 0. So here, so that means some element is in A, in B, in C, and so on. When C 0, it is not. Okay, let's do this. So B intersection C. Okay, so here B and C. So when it is both, when some element in both, then it's true. Okay, so here's B and C. It is 1. This is not 0. Why? Because they are not the same. They are not the same. Oh, here's they are the same. They are not the same, so it's 0. You get the point. Okay, so we get B intersection C. So now we have B intersection C. We're going to see with or with A. So we're going to look at this column and this column. If either one is 1, we're going to put 1. And here we put 1. And here is 1. Why? Because without even looking at this one, you can see here all these should be 1. Done. I don't have even to look. But then maybe after here, I'm going to put 1 here because it's 1 here. And you can see 0, 0, 0, 0. Just this is my result. Okay. So A union B. Okay. So again, the very first 4 will be, I just go ahead and copy them. And then from here, I'm going to say, okay, 1, 1, you can see them. And the last two are zeros, right? I do the same thing for everyone. So I end up, now I'm going to be looking, when I'm done, I'm going to be looking about the final result. What the final result is that represent this and represent this operation. Okay, where you see them here, and you see them here. Okay, these are the final. So I'm going to compare these. All right. So when I compare what I see, are they the same here? Yes, they are. Second row, they are the same. Third, and so on. You can see they are exactly the same. So what that tell me? They are in fact equal.